Hello everyone. Today we are going to derive the three-moment equation. The three-moment equation is a single algebraic expression that relates the moment values at three consecutive points in a beam. This method is used for the analysis of the continuous beams. This equation was derived by a French engineer, Emile Clapeyron, in 1857. So it is also called the Clapeyron's theorem of three moments. Now let us start deriving this equation. Let us consider two adjoining spans AB and BC in a continuous beam with unequal settlement of supports. You can see that the supports A, B and C are not in the same level. In this continuous beam, let us keep span AB is equal to L1. Moment of inertia for AB is equal to I1. Span BC is equal to L2. Moment of inertia for BC is equal to I2. The vertical distance between the support A and B is equal to HA. The vertical distance between the supports C and B is equal to HC. From the point B, let us make one tangent on the left side and the right side. You can see that I have made a tangent on the left side and the right side. Then let us make one horizontal line. The horizontal line is A1B C1. The tangent line is A2B C2. With respect to the horizontal line, we are making two angles from the tangent, theta BA and theta BC. Now let us find tan theta BA. We know the tan theta formula, opposite side by adjacent side. The opposite side is A1, A2. The adjacent side is L1. So A1, A2 by L1. In the same way, let us make tan theta BC, which is equal to C1, C2 upon L2. The angles theta BA and theta BC are very small. So tan theta BA will be approximately equal to theta BA and tan theta BC will be approximately equal to theta BC. In this case, we will get theta BA is equal to A1 A2 by L1, theta BC is equal to C1 C2 by L2. We can clearly see that theta BA and theta BC are same. So we can write theta BA is equal to theta BC. For theta BA, we can apply this value, and for theta BC, we can apply this value. A1 A2 is equal to HA minus AA2. C1 C2 is equal to CC2 minus HC. AA2 is the deflection YAB, which is developed due to the tangent we made in the point B. So instead of AA2, we can apply YAB. CC2 is the deflection YCB. So for CC2, let us apply YCB. Let us split this into two values. Also let us split this one into two values. So in this equation, if we calculate YAB and YCB, we can make the three moment equation. So let us find YAB and YCB. In the continuous beam, let us make the bending moment diagram. This bending moment diagram is due to the external loads. It will be positive because it is sagging. When we draw the bending moment diagram due to external loads, we have to assume each span is a simply supported beam. So we have to make separate diagrams. This is for the first span and this is for the second span. This bending moment diagram is due to the unknown moments at the supports. It will be negative because it is hogging. In the support A, there is a moment MA. In the support B, there is a moment MB. In the support C, there is a moment MC. Now let us calculate the deflections using moment area method. First, let us apply the moment area method in the first span. In this method, we have to divide the moments by EI. Here, we do not know the exact shape of the bending moment diagram. It may be a point load or UDL, we do not know. So, we can't find the area. So, let us keep this as area 1. Now, let us find the deflection in the span AB, that is YAB. For that, we have to multiply the area with the centroid. The centroid distance should be made in the left side. You can see that all the centroids are taken on the left side. Here the area is A1 upon EI1. The centroid we do not know, so let us keep the centroid as x bar left because we are calculating the centroid on the left side. When we multiply the area with the centroid, we are getting this. In this diagram, for the span AB, let us separate into two triangles by the dotted lines. You can see that now we are having two triangles. First, let us consider this triangle. We know the triangle area formula half into breadth into height. For this triangle, the breadth is MA by EI1, the height is L1. So for the area, we are getting this. The centroid towards the left side is L1 by 3. We can apply that. Now let us consider this triangle. For this triangle, the breadth is L1 and the height is MB by EI1. So for the area, we are getting this. The centroid towards the left side is 2L1 by 3. We can apply that. In this equation, EI1 is common. We can take this outside. We can multiply 2 with 3. We will get a 6. We can cut this 2 and this 2. Here we will have 3. L1 into L1, we will get L1 square. Also L1 into L1, we will get L1 square. In this equation, actually we need YAB by L1. So let us divide YAB by L1. When we divide, here we will get A1 x bar L by L1. Here this square and here this square will be eliminated. Finally, we will get this. Now let us find the deflection in the second span, that is YCB. In this span, the length is L2 and the moment of inertia is I2. The centroid should be taken on the right side. You can see that all of the centroids are taken on the right side. For this diagram, we do not know the shape of the bending moment diagram. So let us keep this as area 2. In this diagram, let us calculate the moment area. For that, we have to multiply the area with the centroid. The area is A2 by EI2 and the centroid is x bar right. We can apply that. For this diagram, here also let us split as two triangles. For this triangle, the breadth is MC upon EI2, the height is L2, So for the area, we are getting this. The centroid towards the right is L2 by 3. We can apply that. For this triangle, the height is MB by EI2. The breadth is L2. For the area, we are getting this. The centroid towards the right is 2L2 by 3. We can apply that. When we multiply 2 with 3, we will get a 6. We can eliminate this 2 and this 2. Finally, we will have 3. L2 into L2, we will get L2 square. Here also L2 into L2, we will get L2 square. EI2 is common. We can take it outside. In this equation, actually we want YCB by L2. So let us divide YCB by L2. When we divide A2 x bar R by L2, we are getting this. Here this square and this square will be eliminated. Finally, for YCB by L2, we are getting this. In this equation, let us apply the values of YAB upon L1 and YCB upon L2. After applying, we are getting this. Then we can rearrange the values. We can keep HA by L1 and HC by L2 on one side. For that, we can take this on the left side, so it will be positive. Then we can keep these two terms on one side. Let us take this negative value on the right side, so it will be positive. Finally, we are getting this. E is common in both of these terms. We can take on the right side, so it will come in the numerator. Then let us multiply 1 by I1 with these values and 1 by I2 with these values. After multiplying, we are getting these. Then let us take these two values on the right side. When we take them on the right side, they will become negative. Here and here, MB and 3 are common. We can take them outside. Then let us multiply by 6 on both of the sides. When we multiply 6 with this value, this 6 will be eliminated. When we multiply by 6 here, 6 by 3, we will get a 2. When we multiply with 6 here, this 6 will be eliminated. When we multiply by 6, these terms, we will have 6 on the numerator. Finally, we have derived the three-moment equation. Suppose I1 and I2 are equal to I and there is no settlement, which means HA is equal to 0, HC is equal to 0. This equation will be changed to this equation because when we apply HA is equal to 0 and HC is equal to 0, these two terms will be eliminated. When I1 is equal to I2 is equal to I, here and here I will be eliminated. So finally we will have a new equation. Now let us make the formulas for 6a1 x bar L upon L1, 6a2 x bar R upon L2 for the standard cases. Now let us see the first case when the point load is acting on the center. When the point load acts on the center in a simply supported beam, we will have the bending moment diagram like a triangle. The maximum bending moment in the center is WL by 4. Now let us calculate the area of the bending moment diagram. This is a triangle. We know the formula for the area of the triangle, half into breadth into height. For this triangle, the breadth is L, the height is WL upon 4. We can apply that. When we apply, we are getting WL square by 8. This triangle is symmetrical, So we can easily calculate the centroid. The centroid to the left side and the right side are L by 2. Now let us calculate 6a x bar left upon L and 6a x bar right upon L. Finally, we are getting 3wl square by 8. Since this triangle is symmetrical, we are getting the same value for the left side and right side. Now let us see the second case when the point load is acting at a distance of A from the left support. We know that when the point load is acting at a distance of A, the formula for maximum bending moment in a simply supported beam under the point load is WAB by L. This is also a triangle. We can calculate the area easily. The formula for area is half into breadth into height. The breadth is L, the height is WAB by L. We can apply. Finally, we are getting WAB by 2. This triangle is not symmetrical, so the centroid to the left and right are not same. To the left, the centroid distance is L plus A by 3. To the right, the centroid distance is L plus B by 3. Now, let us calculate 6a x bar L upon L. We have already calculated the area we can apply. The centroid is L plus A by 3. B is equal to L minus A. So instead of B, let us apply L minus A. For L minus A and L plus A, let us apply the formula A square minus B square is equal to A plus B into A minus B. Using the formula, we are getting L square minus A square. Finally, we have calculated 6a x bar L upon L, which is equal to WA by L into L square minus A square. Now, let us find 6a x bar right upon L. The area is same, but the centroid distance is different. Now, we have to take the centroid distance on the right side, that is L plus B by 3. Let us apply the centroid value in the formula. We know that A is equal to L minus B. Instead of A, let us apply L minus B. L minus B into L plus B, we will get L square minus B square. Finally, we have made a formula for 6a x bar right upon L, which is equal to WB by L into L square minus B square. Now let us see the next condition when the uniformly distributed load is acting for the full span. When the uniformly distributed load is acting for the full span, the bending moment formula in the center of a simply supported beam is WL square by 8. Now let us calculate the area of the bending moment diagram. This is a parabola made by second degree curve. The formula for area is 2 by 3 into breadth into height. The breadth is L, the height is WL square by 8. Finally, we are getting WL cube by 12. This is a symmetrical diagram. So, the centroid lies at a distance of L by 2 from the right side and left side. So, x bar left and x bar right are having the same value, L by 2. Now let us calculate 6a x bar left upon L and 6a x bar right upon L. Both of the values will be same because we are having the same centroid distance. In this formula, we can apply the values of area and the centroid. Finally, we are getting WL cube by 4. Now let us see the next case. Decreasing triangular load on the whole span. This is a triangular load. Also, it is called as a uniformly varying load. If this UVL is acting on the simply supported beam, the reactions will be WL by 6 and WL by 3. Here we have to draw two bending moment diagrams, otherwise it will be very difficult to make the formulas. We are going to find the moment in the point B. Before the point B, there are two loads. The reaction in the point A, WL by 6, then the UVL. So there are two loads. The reaction in the point A is acting towards the point B in the clockwise direction. So it will be positive and the distance is L. So WL by 6 into L, we will get WL square by 6. The shape of the bending moment diagram will be a triangle. Now let us draw the bending moment due to the UVL. This UVL is acting towards the point B in the anti-clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid. This is a triangle, so the area formula is half into breadth into height. The breadth is L, the height is W. So for the area, we are getting minus 1 by 2 into W into L. We are taking moment about the right side, so the centroid is 1 by 3 into L. We can apply that. After the simplification, we are getting minus WL square by 6. This diagram is in the parabolic shape. This parabolic is made of the third degree curve. Now let us find AX bar L. For that, we have to multiply the area with the centroid. For this triangle, we know that the area formula half into breadth into height and the centroid is equal to 2L by 3. After simplification, we will get WL power 4 by 18. For this parabola, the area formula is 1 by 4 into breadth into height. Also, it should be negative. The centroid to the left side is 4 by 5 into L. After simplification, we are getting WL power 4 by 30. Finally, for AX bar L, we are getting WL power 4 by 45. Now let us find 6A X bar L by L. When we simplify, we are getting this value. For our own convenience, let us multiply the numerator and denominator by 4. After multiplying, we are getting 8WL power 3 by 60. Now let us find A X bar right. The area formula is same, but the centroid is only different because we are taking on the right side. For the triangle, the centroid is L by 3. For the parabola, the centroid to the right is L by 5. After the simplification, we are getting 7WL power 4 upon 360. Now let us calculate 6A X bar right upon L. Finally, we are getting 7WL power 4 by 60. Now let us see the next case. Isosceles triangle load over the entire span. The reactions in the point A and in the point B will be WL by 4 and the maximum bending moment on the center will be WL square by 12. In the bending moment diagram, let us make two sections, one section on the left side and one section on the right side. The first section at a distance of x and at a height of y. The second section at a distance of x dash and at a height of y dash. Let us consider the half span. Half span is L by 2. To calculate the intensity of the loading with respect to x, we have to divide Wx by the half span L by 2. Finally, we are getting 2Wx upon L. Y is the moment at the distance of x. So let us calculate y. This reaction is acting towards the section in the clockwise direction, so it will be positive and the distance is x. So WL by 4 into x. For the UVL, we have to multiply the centroid with the area. The area is half into breadth into height. For the height, we have already calculated the intensity of the loading. We can apply that. We are calculating movement towards the right side. So the centroid will be 1 by 3 into x. Finally, we are getting this. In the same way, we can calculate ordinate y dash. Now let us find Ax bar L. The formula is here. Integration of xy dx plus integration of L minus x dash into y dash dx dash. The limit for the first integration is 0 to L by 2 and for the second integration also 0 to L by 2. We have already formed y and y dash. We can apply in the integration. So we are having two integrations. First, let us do this integration. When we integrate x square, we will get x cube by 3. When we integrate x power 4, we will get x power 5 by 5. We can take a w outside because it is constant. Then let us apply the limits. No need to apply the zero limit because the whole term will become 0. Only apply the upper limit. When we apply the upper limit L by 2 instead of x, we are getting this. After the simplification, we are getting WL power 4 by 120. Now let us make the second integration. Here we have to multiply these two values. When we multiply, we are getting this. Then we can make the integration. After making the integration, we can apply the limits. No need to apply the lower limit, only apply the upper limit. After the simplification, we are getting 17 WL power 4 upon 960. We have calculated both of the integrations. We can add them. After adding, we are getting this value. Ax bar L and Ax bar right will be equal because it is a symmetrical diagram. Now let us calculate 6a x bar left by L and 6a x bar right by L. After the simplification, we are getting 5WL power 3 by 32. Now let us see the next case, movement at any point on the beam. You can see that a clockwise movement is acting at a distance of A from the point A. The reaction in the point A is m upon L, but it will be acting downwards. Now let us make the bending moment diagram. First, let us make the bending moment diagram because of the movement. This movement is acting in the clockwise direction, so it will be positive. And the bending moment diagram will be a rectangle. The reaction in the point A is acting towards the point B in the anti-clockwise direction, so it will be negative and the distance is L. We can eliminate this L and this L. Finally, we are getting minus m. Since we are getting a negative value, we have to mark as negative. This diagram is a triangular shaped diagram. Now let us calculate area into x bar left. This is a rectangle. We can easily calculate the area. The area is b into m. This rectangle is symmetrical, so the centroid lies in the center. The centroid will be b by 2, but we are calculating the centroid on the left side, so we have to add this a. So the distance from the centroid is b by 2 plus a. We know the area for triangle half into breadth into height. The centroid to the left is 2l by 3. We know that b is equal to l minus a. So instead of B, let us apply L minus A. Here we can take LCM. The LCM is 2. Finally, we are getting this. Here we can eliminate 2. Finally, we will have ml square by 3. Again, for B, let us apply L minus A. L minus A plus 2A, we will get L plus A. We can take M outside. For L minus A and L plus A, let us apply A square minus B square formula. Then we will get these. For these two values, let us take LCM. 6 is the LCM. 3L square minus 2L square, we will get L square. Then let us take the negative sign on the outside. Finally, we are getting this. Now let us find 6a x bar L upon L. This 6 and this 6 will be eliminated. Finally, we are getting this value. Now let us calculate a x bar right. We have already seen the area formula. Let us calculate the distance from the centroid. Now we are calculating the centroid on the right side. For this, the centroid is b by 2. For the triangle, the centroid is L by 3. We can apply that. Finally, we are getting this. Let us take the m outside. Then let us take LCM. Finally, we are getting this. Now let us calculate 6a x bar right by L. This 6 and this 6 will be eliminated. Finally, we are getting this. Suppose UDL is acting at a distance of A from the left support and at a distance of C from the right support. The formulas are here. This is a very complicated formula, so I haven't done any derivation. Now let us tabulate the formulas. These formulas are very useful in analysis of the continuous beams. Now we are going to end this session. Thank you for watching this video.